Um, Give me some down, please. So we're going to use the fabrication methods, yeah, and the toolbox we talked about. You know another trick? Oh, you coming for a trick? So all the fabrication techniques will be reused, but I'm not going to explicitly explain all the fabrication steps. So we use them, the fabrication techniques we talked about as a toolbox now to make devices. And, I like to start by doing or making a few general remarks about sensors, not specific to one particular sensor, but that is more generic. So, first of all, what is a sensor and what is a transducer? They are often used interchangeable, these two terms, yeah. But if you are a little bit more precise, which we are of course trying to be, then they are in a way different things. So a transducer has an input from one of those domains. Physical, chemical, optical, electrical, radiation, temperature, whatever. And it has an output which is typically from another or in another domain. Okay, so some of the domains here appear twice, yeah, but usually it's from an input domain and the output domain. Well, in most of the cases it's electrical, sometimes it's optical, but at the end of the day you want to have some electrical signal which you maybe can display, or it's an optical thing if you really having a display, yeah? You can argue it's an optical output, but if you look at this here, then a transducer is really an energy converter. So you have some sort of signal which of course has an energy, and it translates it to a different domain. Now, of course, this can also go from, let's say, the electrical domain to, I don't know, physical or a radiation. So that means a transducer is also something that converts electrical energy into, let's say, mechanical energy. So transducer is really an energy converter. And if we look now at a sensor, there, yeah, it's really then coming from these different domains here, and it really has as an output an electrical signal, and maybe optical as well, if it's a display, but usually it's an electrical signal. And then it could be also going from electrical to electrical. If you want to measure the resistance of a resistor, then it's an electrical property which is converted into an electrical signal on a display on your multimeter. So that's also a sensor. Now, in the context of the course, we're talking mainly here about physical inputs. So physical quantities that can be measured, converted to an electrical signal, and this electrical signal gives you then a measure of how much of this physical input there is. So pressure, acceleration, sound. Well, sound is a special type of pressure, special case of pressure, rate of turn, force. So that's being converted by a sensor into an electrical signal. And then I mentioned already that you also can go from the electrical domain into an output, which is non-electrical and mechanical, of force. That's what we usually call an actuator. So an electrical motor, for example, is an actuator. And in the microdomain, well, we talked about motors there. Motors are not a very good idea because of the issue of friction. But you can do this in different ways with compliant mechanisms. You can use electrostatic forces, you can use thermal forces, thermal expansion forces, for example. You can use piezoelectric conversion and so on. Okay, so the other point to make, if we stay now with the sensors, is well, we have an input signal we want to measure. Let's stick with pressure as an example. And this is sometimes called the major input or the main input. That's actually what you want to measure. And your output should be strictly proportional to this major input. So your output electrical signal gives you a strict proportionality to whatever the input pressure is. So a strict proportionality is, yeah, well, it's a straight line. If I have here pressure, and here, let's do the other way around. Here I have my pressure, and here I have my output. That's a voltage, and ideally there should be a straight line. Now, unfortunately, this is a very much an idealized case, and it's never like that. There will be some maximum pressure, for example, above which your sensor will not measure pressure anymore. So if you have your little pressure sensor and you stick it maybe into the tire of your car, that goes up to maybe 3 bar or 4 bar. Great, that works up to typical tire pressures. But if you take this thing and you put this into some sort of hydraulic press, then this linear relationship will not hold anymore. So at some point you will have something like where it saturates at some maximum pressure. The other point to make is that your nice linear relationship here is the output, the V, that means it's only a function of your pressure. That's the ideal case. Now, again, this is very much an idealized case, and in reality, it's never the case. In reality, any sensor has other quantities that play a role and disturb your output signal or have an influence on your output signal. One of the major ones is, of course, temperature. So any sensor you build, no matter how much effort you put into your design, you always will build a temperature sensor as well. Now sometimes you want that. If you want to build a temperature sensor, great. But for any other sensors, like pressure sensor, if I measure the same pressure, let's say of 2 bar at minus 20 degree, and again I have 2 bar at plus 50 degree or whatever, then I will be, so let's say this is the 2 bar point. The 2 points I will get, let's say this is for minus 20, and for plus 50 I will lie here somewhere. So the temperature will always play a role. It's usually an undesired property. Usually something you want to get rid of. But this is easier said than done. So temperature here. Then the time, what does that mean? Well, if I measure it in the morning at 8 o'clock and in the afternoon at 4 o'clock, do I get the same values? Yeah, probably. But if I measure it over the course of a year, same pressure, let's say I have exactly 2 bar, and I measure over the course of a year, then I probably will get also an influence over time, so T being temperature and little t being time. So that means over the course of a longer period, your signal, any sensor, will drift away. That's called drift. Now, where is this a particular problem? Well, imagine you have a medical implant. You stick this somewhere inside your body for medical reasons. And to give you a concrete example, we worked a few years ago on pressure sensors that could measure the pressure inside of your eyeball. So these pressure sensors are being packaged, of course, biocompatibly packaged, and then they're being, with a small operation, stuck into a patient that suffers from glaucoma, that causes increased pressure in the eyeball. So it's a small operation, it's being stuck in there. And now the patient has the possibility to monitor the intraocular, inside the eye, pressure with a handheld device. Communication is done wirelessly, and the power in this case was also supplied wirelessly. And you could measure the pressure. And if this pressure is getting too high, you can take medication. Okay, that's great, no? Because the patient doesn't have to go to the doctor every 3 days, because you have to monitor this disease fairly with a good spatial resolution. If you don't do this, you lose eventually your eyesight. So with such an implanted pressure sensor, great. I can measure this every hour if I want with my mobile phone or something similar. But this requires, of course, the output, the pressure output, your display, to be stable over time. Because let's say your pressure inside of the eyeball is, I'm just making up a number, 1.1 bar, and it stays constant, so you have no medical problem. And then suddenly the pressure sensor indicates it's 1.2 bar. Yeah, is this now due to an actual increase of your intraocular pressure, or is this due to an influence of the time over a period of time. You have the sensor implanted in your eye. And that's a major problem for medical implants. And why? Well, because of course you can't take in and out an implanted pressure sensor in your eyeball every week or so, and recalibrate this. So, why do they drift? Well, there are all sorts of mechanisms. The packaging absorbs a bit of vapor, the water molecules. There's a slight swelling of the packaging material. Think of this Parylene coating I showed you not last week, 2 weeks ago. So that absorbs water over time a little bit. And these things, they can cause the pressure sensor to drift away even if the pressure itself is constant. So here you have a time influence. And here there's another one given here, the supply voltage. Well, usually this conversion from the input to the output requires some sort of interface circuitry, and the interface circuitry will also have an influence on the output if the supply voltage slightly changes. This is maybe the least severe one, because circuit design is something we have a lot of experience in, and that can be handled with this. But the other two, temperature and time, so this drift behavior over time, these are really still very active areas of research, in particular for implantable devices, medical devices, where you can't really check quickly, is my sensor now faulty in the sense that it drifts away, or the temperature influence is very severe, or is it actually the major input? So the output you get is the true value, and this true value has always an error to it. And this error you cannot distinguish from the true value. If you knew the true value, you don't have to measure it. That's a circular argument. Okay, so a couple of other things. So linearity errors. This could be that this is not a straight line, but it's I don't know, a little bit bent. Or something like this. I exaggerate here. For whatever reason, so you don't have a pure linear relationship. Hysteresis, that means if I go up and down with my pressure, then I don't exactly go up and down on the same line. That's also quite a common problem in sensors. Repeatability, well, this is kind of this T here. And often these things are drift. I talked about already quite at length. And often these things are difficult to explain analytically. You have different materials involved, they have different expansion coefficients, and this behavior over time, over a year or something like that is, try to analytically capture this and model this and describe this mathematically from first principle, from the physical point of view. Yeah, good luck. So nobody has figured this out to a sufficient degree. Okay, what else to say in general about sensors? A couple of definitions here. So we have accuracy, the accuracy quantity that characterizes the capacity of a measuring instrument, that's your sensor, for giving the results close to the true value of the measured quantity. And here already you run into this problem. Well, what is the true result? Nobody knows this. So if you look at this here, the true value here, it's assumed that you know this. But of course you don't know it. So it's a hypothetical scenario here. And this is just to illustrate these two definitions, accuracy and precision. The precision is then the quality that characterizes the capability of a measuring instrument, the sensor, for giving repeatable results. So here is the true value, and you measure, you have an offset here between these two, but at least it's repeatable. And if you know this, by comparing to, well, maybe somebody has made a better sensor before you already, that's something you can actually, such a, this accuracy, if it's having a high precision, well, that's something you can actually easily solve. You compare this to a gold standard, to a more expensive sensor, to a better sensor, whatever, a bigger sensor. You stay with the medical, if you, let's say you have a reference sensor that is larger, but we know it's very accurate, and you have a gold standard, and you get this sort of behavior here, then that's easy to solve, because I know this difference, and I can simply deduct here whatever millivolt this difference here represents. So this would be an example of low accuracy and high precision, whereas here we have well, we have high accuracy because we are very close to the true value most of the time, but sometimes I have low precision, so it fluctuates around. So this would be low precision sensing. This of course has to do with noise as well in your output system. And noise is a very complicated topic because you have many different noise sources. You have noise in the electrical domain, in the mechanical domain. You have noise from your A to D conversion that is going on at some point. So noise is always a good topic if you want to bring people into trouble in a thesis defense or something. But it's a very difficult topic, and of course very important topic. And finally, we have the sensitivity here. Sensitivity is usually defined by the slope of your output with respect to the input. So the sensitivity in my trivial example here is basically the slope. Now I can define here a sensitivity overall. I can say, okay, I take here this point, and then I take this point, and I calculate the sensitivity. If this is really proportional, then it's correct. But I can also define a sensitivity if I have a nonlinear behavior at a certain point. So the sensitivity also can change according to the input quantity. So if I'm here somewhere, the sensitivity suddenly becomes much smaller. Okay, so these were a couple of general remarks. Now I want to spend probably the remainder of today's lecture on resistive sensing. Resistive sensing is one of the most common transduction principles. So meaning that I have an input quantity, pressure, I stay with that, but it could be many other quantities that causes, for whatever reason, a change in resistance in a certain material over a certain geometry. And this change in resistance I can measure, and this gives me then my output signal. And what changes resistance? Well, that's listed here. So we have geometry effects. So the shape somehow gets varied. Then I have material intrinsic effects. That the this is called the piezoresistive effect. So the resistivity, which is a material property, changes with usually mechanical stress. Okay? And these two are most widely used in the MEMS world. Then you have also temperature effects. So that the temperature affects the resistance of a material. And with this you can build temperature sensors. So in this case, you don't run into this problem that you have an unwanted temperature change. And there are a couple of other effects that also influence or change the resistance, like photonic effects used in the photocell, magnetic effects used in a giant magnetic resistance device, and also chemical effects that are being used for gas sensors. So these I will not talk about here in the lecture. We're going to talk mainly about geometrical and piezoresistive effects now. Okay, piezoresistive effects. So there are two that should be discussed. The first is simply due to a geometry change. So recall this equation here. So the resistance of a piece of material, I have a bar of a material, and this has a length L, and it has a cross section A, and A is given by well, A times B if these are the side lengths of this bar of material. So that's A, the length is L, and then you have this material constant, which is rho, and that's the resistivity. So that is really a material property. Resistivity, if you look at the units here, is in ohm centimeter or ohm meter. Simple to see if you do a dimensional analysis. Length is meter or centimeter, and A is meters squared. And that's as I said, a material property, and now it depends on the material. For a lot of material, this resistivity is to first order approximation constant with mechanical stress. There are some materials where it's not constant. So we're going to talk first about the case where the resistivity is constant. Most metals fall into this category. So we assume for now this raw resistivity is not a function of a mechanical deformation. So now imagine this bar of material. There is a force now pulling on this, right? And if I pull on this material, then I will get an elongation here. It gets a bit longer. So it changes its shape, it gets a bit longer. So L will be now an L plus a DL. It's a bit longer. And of course, how much longer it gets, that's again dependent on the material itself. How much you can stretch it. If you take a rubber band, a bit of pulling, you extend it quite a lot. If you take a metal bar, you pull on it, you don't see anything, but it still gets longer. Doesn't mean that you don't see anything, it doesn't get longer. Now, if it gets a bit longer, what happens to A? Does it stay the same? It gets smaller, huh?
Yep.
It gets smaller because you don't create any new mass here of your material. You don't add more atoms to your bar of, let's say, metal here. So somehow it has to get thinner. So the A gets smaller. Okay? And there's a relationship between these two, which is usually described by V. That's the Poisson's ratio. I think I've got this on a slide to come. So this V, this describes how much it gets longer and how much it gets slimmer, cross-sectional area. That's the Poisson's ratio. Okay. Okay. Then what we have is the gauge factor. So American spelling, you see this also without the U. The English, British spelling is with a U. It's not a gauge. It's a gauge factor. This gauge factor is defined as, so how much does the resistance change, right? dr referred back to the resistance before I pulled, divided by R. And this ratio goes over another ratio divided by GL over L. So that's how much it gets longer, also referred back to the original length. And as I said, we are assuming that the resistivity rho is unchanged. Okay. So that's in a nutshell the theory, and how do you practically implement this? Well, you usually do something like here, where I don't have one bar, but I try to make this effect be more pronounced, so this dr larger, and this is a simple geometry trick, where I just fold this around a few times, so I get here, well, how many meanders? Meander like a river, winding river. So you have 1, 2, 3, 4, 5, 6, 7, 8. So this effect of the resistance change is multiplied by 8. And then there's a number here. So for typical metals, thin film metals, how thin is thin? A couple of micrometers, let's say. So here my original thickness would be a couple of micrometers maybe. There I get here a gauge factor. This is sort of the figure of merit of about 2 for most metals. You can maybe go up to 3, and some are below 2, and so on. So this was this really state of the art for a long time until maybe in the 1970s. Yeah, gauge factor of 2. Now, compared with modern technology, this gives you low sensitivity. So, if you now exchange here resistance with force, because that's what you want to measure at the end of the day, mechanical elongation. My slope here would be rather low if you compare it to a modern resistance change sensor, to which I come in a bit later. There's another important definition which we'll be using later on quite a bit. Just make note of that. So this here, this direction, that's parallel or longitudinal, or longitude direction. Right? So this is along my block here, and then of course here orthogonal or transverse is perpendicular, so in this direction. So just make a mental note of this because we need this later. Okay, so just to show you a few examples, here is a real thing. Yeah? You have encapsulation and a substrate where you have these meanders on. You have some contacts, and between these contacts there, you measure then the resistance. Where they're being used, many different shapes and forms and so on, but they all work on the same principle. So, for example, if you have here a shaft or a rod of a motor, you glue this on here, and then you can measure the mechanical strain or stress. Strain, stress are proportional to each other. To a good approximation for a metal that is not plastically deformed. If we are in the elastic regime, stress and strain are proportional to each other. Here is a table. What kind of metals do you use? Now, they are usually alloys. One of the most commonly used is Constantan, gauge factor 2.1. If you use some other ones, you go a bit higher. Now, Constantan is nickel and copper in a certain ratio. Why is this popular? Well, it has a very low temperature dependence. This is where the name comes from, constant. Constantan. It's not 100% constant with temperature, or has low temperature resistivity, but it's a good approximation. It's the best, one of the best materials with this property. So that's one way to minimize this influence of T. So this is how the cross-section would look like of such a strain gauge. So here is your substrate, so this is where you want to measure the stress in mechanical shaft, let's say, of the motor, or the wings of an airplane, or many other applications. Now you have to glue your strain gauge with some sort of, usually some epoxy. And then here is your actual strain gauge that sits on a foil. The entire thing is encapsulated by a protective coating. That's often another layer of epoxy. You have to make electrical contact, so you have to somehow solder to it and have a wire sticking out here, where you, well, 2 wires sticking out there where you can now measure the resistance. So that was state of the art until the 1970s. This has many disadvantages. Well, first of all, you don't measure really your mechanical stress or strain in the substrate, but a distance, it's called E here in this drawing, above the substrate. Now, in many applications this may be negligible or the same, but in some others this may play a role. Then, of course, you have this dreaded temperature problem. And this is here quite severe because you have quite a bit of different materials. And all these different materials have, of course, different thermal expansion coefficients. So if it gets hotter, they expand at a different rate, and therefore the temperature generates also mechanical stress. Mechanical stress in your assembly here. And that's, you don't want to measure this. You want to measure the stress in here. So yeah, one way is to use this Constantan alloy, but that doesn't get around the problem of the other materials. And this is, yeah, if you look at these pictures here before, this is relatively large. So if we go to the micro world, yeah, not a very suitable approach. The next step was actually to go into silicon. So in the 1970s, people started using silicon now as a strain gauge. And here it shows you a typical setup. One of the problem here is that you have to have an electrical signal, so you have to have some current flowing in here and current flowing out there. So you need to isolate, electrically insulate your current path here from the substrate. Now, the simple solution is here to make a PN junction that is reverse biased or zero biased, well, not forward biased, let's put it this way. And then you can do that. You use here silicon dioxide as an insulation layer, aluminium as contacts here, and the real thing looks like this, for example. So here is your silicon strain gauge. Now, in silicon, you have 2 effects now. In silicon, you also have this effect that it gets a bit longer and the cross-section gets a bit smaller, but this effect is rather small. So why use silicon in the first place? Well, the answer is given in this equation here. And one of the material properties of silicon, in contrast to metal, is that the resistivity actually changes. The resistivity changes with here the mechanical strain, so how much elongation you have here. Yeah? And it's proportional to E, so Young's modulus, elasticity of silicon, and some factor which is usually called pi. This is, if you see this the first time, it's rather confusing. This is not 3.14. This is an abbreviation for a factor, nothing to do with the circumference of a circle. Okay? So we'll come back to this in a second. So this was is an example of a real thing. Here's another example of a company called PCM Sensors, where you can buy them, and you can still buy them today. So that's was a successful development. So you can call this one of the first MEMS sensors in a way. Another aspect here is that the doping of the silicon has a strong influence on how much change you get, how much change in resistance. There's a figure of merit, which is it's a complicated parameter, which I spare you the mathematics. If you're interested in this, you can read up a paper, which is referenced on the next slides. It's a figure of merit, how much change of resistance you can expect. And what you see here are two things. First of all, it's very much a function of the doping. And it's secondly also a strong function of the temperature. So here we have already a problem again. Temperature comes in here again. And this is for P-type silicon, a very similar curve you get for N-type silicon. So both doped silicon N as well as P-type are piezoresistant. Typically what's being used is a lightly doped silicon as well, P or N. Because if you dope it too high, you see these curves here drop quite significantly. So usually you operate somewhere around here. So you use a lightly doped silicon if you want to make a piezo-resistive sensor. Now, how much change do I get? So here we have two cases. So I have here my delta R over R, and the previous slide it was dr over R, and it's the same thing. And I have, in the general case, I have here, well, longitudinal, I explained already. So I have longitudinal strain, and I have transversal strain. And I can always express my change in resistance as a sum of longitudinal and transversal stress, and each of the stress values is being multiplied by this pi, and this is an indices now. Be careful, this is not the same. This is T for transversal, this is L for longitudinal. Okay. But not very clear on the slide. The other point to make is if I, let's say I have here purely longitudinal force or stress, because I shrink, I get slimmer here, I also introduce always a transversal component. Because my material shrinks and it's embedded in a crystal. So if I go back here, if this here is my the red, dark red is It's the bar here on the blackboard. But this is embedded, of course, in a silicon crystal. So it can't just shrink as it wants. But because the neighboring atoms are pulling on it, you always get here also a stress which is perpendicular. So out of the board if you pull in this direction. Okay. So they always have both stress directions, transversal, longitudinal. So this is why we have always these two components there. And the same argument, of course, is if I do this. If I have transversal, it's not that this longitudinal component just disappears. So the question is now, so how do we get this pi t and pi l? Or pi parallel and pi perpendicular? So let me just write this on the board. We have the pi l, and we have the pi t. Use uppercase here. And later on in the slide, I will also use the notation. So this is pi parallel, and this is then pi perpendicular. Okay. So this is something you also see on the slides and also in the literature. So how do we get that? The other thing to take into consideration is, well, this is typically single crystal silicon. Single crystal silicon has directionality because of the planes of the crystal. And therefore, somehow the crystal orientation, which direction you create your silicon piezoresistor also plays a role. So it's a complicated problem, if you think about it. So let's go through this without going into too much mathematical details. How to get this pi L and pi T. So the usual argumentation is to start off by a vector equation where you relate the electric field vector, and we are in a three-dimensional scenario, so we have three components. So here it's called 1, 2, 3, but it could be also x, y, z. And that is being related to the current, the current density, also x, y, z, or 1, 2, 3. And this is related by a matrix which is the resistivity matrix. Okay, so this is effectively Ohm's law here. It's Ohm's law in vector quantity. And the voltage is not the voltage, it's the electric field, and the current is not the current, it's the current density. This is nothing but Ohm's law. And now, what we also can say is, well, let's say I have these six quantities of my resistivity. And we assume, first of all, we have an isotropic conductor. Yeah? So in an isotropic conductor, I can argue that the resistivity coefficients 1, 2, 3 are all equal to rho, and 4, 5, 6, I can argue they are zero. Yeah? That comes from the isotropic property of the material. Now, we are in an anisotropic material. We are in silicon. Yeah? So we're going back to this in a moment. But let's let's assume this. Yeah? And actually, the argument is if you go, as I said, I skip here some steps, and I want to not spend too much time on the mathematics. But if you go into these references here, this assumption about the isotropic behavior of a conductor also holds in a single crystal silicon piece of material, which is anisotropic, as I just said. Yeah? But this holds if you are aligning your piece of silicon along a certain crystal direction. So, for example, this holds if you align your silicon piece of material along the 1, 0, 0 direction. So, one of the main directions in your silicon crystal. Yeah? And so, why this is here? Read these references if you're interested in that. Okay, so we simplify the problem a little bit, and now what we do is we assume a small cube. Somewhere in there, we take an infinitesimal small cube, which is here drawn much larger, but this is a small cube. And now I can define mechanical stresses on each of the faces of my cube. Now we take 3 because the other ones are, of course, the same. Yeah? So we take only 3. And what I have now is I have a component of my mechanical stress, if I take the top surface here, which is of course perpendicular. But I can also have this. I can also have what's called shear stress. So the in-plane stress, torr, that's shear stress. So I have perpendicular stress, and I have shear stress, and it's in the plane, so I have a torr 1 and a torr 2. Okay. Now I can set up an equation that relates the change in resistance normalized to the original, sorry, not resistance, resistivity, big difference. Apologies, resistivity. So change in resistivity, reference to the original resistivity, to these mechanical stresses. In plane, torr, shear stress, and normal stress, sigma. Yeah. And the proportionality constant between that is pi. Yeah. So this is this pi here. So here this turns out not 3.41, but a matrix. Yeah. And if you look at this matrix now, it's a strange matrix. It has a lot of zeros, and it has some coefficients here which are apparently not 0, where you have this part of the matrix, this submatrix is symmetric. So here you have a pi 1, 1, a pi 1, 2, and a pi, I can't read it on my screen, a pi 1, 2, and a pi 1, 2, yeah, exactly. Right? So it's symmetric. And here appears a pi 4, 4. This is actually a tensor, yeah? But I'm not good at tensor equations, and I think you are also not so good at tensor equations, or tensor mathematics. So as I said, I want to spare you this, but I want to give you at least a bit of a flavor of how this works. Now, where are these zeros coming from? Well, these zeros are coming from, some people are extremely good at visualizing silicon. You remember the cube you guys made, we had going round. If you turn this cube in the right way, you find symmetries, of course. And these symmetries, they result in that here in this tensor you have a lot of zeros. Luckily. One more point maybe to make is, so here I have a Tor 1 and 2, and I have a 2 and 3 here. So how do I know that this Tor 2 is equal to this Tor 2? It's also not obvious. Yeah, again, it comes from the same argumentation. It comes also from this symmetry in a single crystal lattice. So this is how deep I want to go into it. So I'm not going to ask you as in the exam, so explain to me why this Tor 3 is different to the Tor 2, and why is the Tor 2 on the side facing you the same as the one on the top. So if you're interested in this, by all means go ahead and go into literature, read the references that on the previous slide. If I read this, I get a headache. Some people like that. Okay, so we'll leave it at that from the discussion, at least from my side, and I don't expect you to know more, of course, what I explained here in the lecture. Now, but we're still not there. We're still not at this longitudinal or parallel or transversal or perpendicular coefficient. So, how do we get there? Well, the answer is on this slide. Now, it depends on if I make a silicon piezoresistor, in which direction I put my silicon piezoresistor in my overall crystal of my silicon lattice. So here we have the longitudinal direction PL and the transverse direction pi t. So pi L, pi t. That's finally now where I wanted to get to. And this pi L and pi t depends now how, as I said, I orientate my piezoresistor in the silicon. So this table here gives you some of the important directions. Of course, if I orientate it in the 1, 0, 0, then the transversal direction is the 0, 1, 0. So that's comes just from the definition of the Miller directions or indices. So and you can go through the table. That's all these directions are, of course, perpendicular to each other. But my pi L and pi t, they vary quite a bit. And they are now combinations of this pi tensor. So the question is, of course, if I make a piezoresistor in silicon, which one do I take? Actually, people have not only figured out these directions, but they have also drawn figures like that. So you see here the piezo resistive coefficient pi L, longitudinal pi T, transversal as a function of directions. Now, of course, this is a function of doping now again, so this is for P doped. At low doping level, this is what I explained in one of the previous slides, so it's relatively moderate doping. If you go to very high doping, all these curves converge, so that's good. And if you want to make a piezoresistor, well, of course, I want to have a relatively high pi T or pi L. So, to place my piezoresistor along the 110 direction, parallel to the 110 direction, or any equivalent directions, is a good idea. It's not a good idea to place it in parallel to the 100 direction. That's not going to give you much piezoresistive response. And you can go further into details. So previous diagram was for P-dope. This is now N-dope silicon. And this comes from, finally, I give a reference here as well. This comes from a classical paper from Kanda from the 1980s. So, one of the most important papers on piezoresistivity. If you want to read this, by all means, but as I said, I will leave it at this level of discussion. So he, for example, also goes through the mathematics. There's a lot of physics. There's the Fermi level plays a role, and so on and so on. Yeah. So again, we'll leave it at this level here. After all, we're engineers and not physicists. Now, but going back to the table here, it still doesn't give me any numbers, of course. So, which one do I take now if I want to practically build something, engineer something? So, the numbers are given here. And there's a circle around the second line here. So, this is P-doped silicon. Typically, you use boron for that. You orientate it along the 110. If you think of these measurement results on the previous slide, if you look at the line above, 100 has very low values. In the graphical representation, it was almost 0, but it's actually a factor of 10 smaller, for pi parallel, even more. This is, by the way, not the case if you go to N-doped silicon. So this is for P-doped, where the 100 is close to 0, the pi L and pi T. But if you look at N-doped silicon, the story is rather different. And indeed, I made a circle here around this line here. But actually, why? Because if I take here N-doped silicon, I get 102 compared to 72, and this is almost the same. So this would give me a higher sensitivity. Any idea why? Nevertheless, this is the P-doped, where the circle is around, is the more preferred way of making piezoresistors. The third line, the third line gives me more sensitivity, no? The other one gives me circled line gives me less sensitivity. No idea? Okay, I'll give you the answer in a moment. So this is doping here, this level, 10 to the 18, that's moderate to low doped. Boron for p-type and for N phosphorus, for example. Okay. So I make the circle around there, I'll tell you why in a minute, but of course you can also make N-type or N-doped piezo resistors. It's also people have used. Okay, let me get back to this, why this is the preferred solution in a minute. And let's think about how we can change, no, sorry, how can we measure the change in resistance first. So we've done all this mathematical stuff to calculate how much my resistance changes. Now, of course, we have to think about how do I actually measure this change in resistance. And this person here helps, Charles Wheatstone. He didn't know about silicon piezoresistive properties, but he also wanted to measure small changes in resistance, and he came up with this ingenious little circuit where basically he has one unknown resistor, and he wants to know what this is. So he makes a circuit, and he puts, let's say, here a strain gauge. So we are back to the original metal strain gauges, but this works for now silicon strain gauges exactly the same way. And oops, yeah. So this is my strain gauge, and now I adjust my resistor so that I get here a voltage. If my Wheatstone bridge is symmetric, this Vm will be 0. Now, if it's not 0, then I can calculate here this Vm. And if all R1 to 4 are the same, then Vm will be 0. And if I have now here a resistor that changes a little bit by delta R, so this is my piezo resistor that has changed a bit due to mechanical stress, then I will get here an output voltage which is given by this equation. So you can do some simple circuit analysis to verify this. And if you look at this now, here I have a factor delta R divided by 2R0. That compared to the 1 here, right, I can say with, well, depends on the numbers, but many applications, the approximation is that I can say, okay, this here is actually small compared to the 1, and therefore I can neglect this factor. And if the animation was done in a better way, this equal sign would change to an approximate sign. So this is often an approximation which is being made if you use this setup where you have one resistor changing by dr or delta. Now, what about if I do this? So what about if I make a circuit or a setup where I don't have one resistor changing, but I have all four changing. So what I have done now here is this one increases, this one increases, this one decreases, and this one decreases. All by the same amount, delta R. Well, I can do the analysis again, and then I get here a very nice, simple equation, which is V, that's the voltage that supplies a signal to the Wheatstone bridge here. And if you compare this here, I have a factor V over 4. So this, of course, here is 4 times as large. My VM is 4 times as large compared to if I have just one active resistor, and I don't have to make an approximation here. So I get 4 times more signal, delta R over R0. So this is my change in resistance, and that's really whenever you can, you use such a configuration where all 4 resistors are changing. They're changing here by the same amount, delta R. So now I go back to my table.
Yeah, because it's the same amount.
And I ask you again now, why do we use the second line here if we are in silicon?
Almost the same amount.
Now you should be able to figure it out, right? Come on. Yeah. So because the p doping gives me the possibility to make the pi parallel and the pi perpendicular, but that gives me the possibility, the pi r and the pi
Almost the same.
t and pi l are opposite and almost equal. 66 and 72, minus 66 and 72. And this is not the case for the n-doped silicon, which I would have to orientate in a different direction, but okay, that's not an issue. Right? So that's the reason why this line, the second line, is the preferred line for piezo-resistive sensing. Yeah? Because I can make here resistors that go up here, plus, and go down, minus, by almost the same. And I can even the 66 and 72, I can twiddle this out by making one a little bit longer. If you want to be even more precise, or a little bit wider or something like that. Okay. So, yeah, you can also do. Maybe I should also mention this. I can also do this. So I could do a half bridge strain gauge circuit where R2 and R3 are not changing and the other two are changing. That's also sometimes done. Yeah, I can make this like that. I can make a dummy gauge here which is not being strained, and so on. So there are a couple of possibilities, but by far the most used one is this configuration, and it has another advantage. It has another nice advantage. Coming back to this problem, T, temperature. Because if you implement this, and we are at the micro scale, so these resistors are close next to each other, they all will see, the first approximation, a similar or the same, or similar is a better word because it's not exact, it's a similar change in temperature. So here temperature change by, let's say, 10 degree will also, this resistor will also see a temperature change by 10 degree. Yeah? So the temperature change is a common mode signal, meaning that it will not influence the VM. Yeah? If all resistors go up by a certain amount, yeah, so if I have a plus in every delta R due to the temperature, not due to my piezoresistive effect, but due to temperature, then my VM will not change. Okay? So that's a common mode signal, and that's therefore a huge advantage in reducing the temperature sensitivity. Because if you remember, you go back, I don't know, 10, 15 slides, there was one curve where you saw a big temperature change in this piezoresistive factor, which was a figure of merit. So one piezoresistor has considerable temperature sensitivity, but with this approach you can actually, to a large extent, eliminate this. You cannot get rid of this totally, but you can minimize it. You can eliminate or alleviate the temperature problem. Okay, now that was the piezoresistive effect, and the last 15 minutes or so I want to spend on showing you how you can apply this now and make a pressure sensor out of it. Yeah? So what we have a pressure sensor. It's a simple membrane that should be thin, should be compliant. And I have a pressure P1 and P2. And if this pressure P1 and P2 is different, so I have a pressure difference, yeah, then my membrane will bend, will deflect. So we put some resistors here. So yeah, this would be a strain gauge. Yeah? You glue it on top of the membrane. So that's 1970 technology. Okay. And then you do this. I put here now 2, but this is because I drawn here a cross section. Yeah? In reality, you would put 4. Yeah? Why? Because we want to make, if possible, a full Wheatstone bridge. And we want to make this small, of course, and if you implant it in your eye, it should be rather small, of course. And you put it in a small hydraulic system, small tubes, it also should be small. And it should be cheap, of course. It should be cost you nothing. Okay, so how can we do this? Well, the first devices, they looked yeah, like this. You have a metal support. You have strain gauges, the meander metal ones. You glue them there, and you make a Wheatstone bridge out of this, and yeah, it works. Order of magnitude 1 centimeter now. Sticking this in your eye is already a problem. Also, it's a serial process, so this is not cheap. If you want to make this really thin here and reproducible and with conventional machining techniques, they cost quite a lot of money. But anyway, now let's think a little bit about this membrane. What's happening there in the mechanical domain if this is being deflected? So this is visualized here. That's a simulation, of course. Let's say we have a round membrane. So here, this is a round membrane. It could be also a square membrane. There's not much difference between the two. But if we now plot the mechanical stress. And here you have two curves. So one is sigma t, and the other one is sigma r. So we had always here the perpendicular and the longitudinal. Here the sigma t is the tangential component. So we are, in a way, we are switching over from Cartesian to spherical coordinates. But the argument is very simple. So I can plot here the stress, well, plot using simulation. I have here a pressure difference, and I can plot here as a function of the position where I am on the round membrane here. I can plot my stress components, the two stress components. And if you look at these curves here, well, interesting. You go from positive to negative at a certain point, which is different for the tangential and the radial component. So if you are positive, that means the material gets stretched. And if you're negative, that will be equivalent to here me turning around the arrow. So you get compressed. So the one is called compressive stress, so being squeezed together, and the other is called tensile stress, if you're being stretched. Okay, but it doesn't matter so much how they are called. The important is that they change sign. So you have here at the edge areas where the material is being stretched, and here in the middle where it's being compressed. Now, where should I put my piezoresistors? The answer is pretty simple, where the stress is the highest. So here at the edge of the membrane, so somewhere there and there. So I get the highest stress. So you can do this mathematically, but again, it's Friday afternoon, late afternoon, so we're not going to do any mathematics anymore. Graphically, you can visualize this. There is thin plate analysis which you can do. You assume you have a thin plate but not zero thickness, and in the middle of your plate you have a neutral stress-free plane. And then you can go into small beam deflection, where if a beam is being bent, so let's say this beam has been bent. Of course, all these diagrams here are grossly exaggerated. You're talking here about minute deflections, and this here in the graphics is grossly exaggerated. But the point for this drawing is that if imagine you have a beam and that is being bent like that, the area there at the surface is being stretched, elongated. So you have here tension or tensile stress, and here actually this curve here is being compressed. So if you go through this beam perpendicular to the length of it, if I go through here, the mechanical stress will change sign as well, from tensile to compressive. And of course you can extend this now to not only a beam but to a plate. You know? So if you look at the cross section now, here, yeah, this is a square membrane. On the previous slide, I had a round membrane. The argument is exactly the same. So I said this already. You have here on the edge, you have the highest stress, and the surface actually at the top, it's tensile, and at the bottom is compressive. And if you go across to the middle, there is just the other way around. Yeah? So it changes from compressive to tensile. And of course my piezo resistors, they will be placed at the top. Usually they're placed at the top. Okay. Now, to make things even more complicated, if you assume now that I make my plate here out of silicon. Silicon is an anisotropic material, so single crystal orientations play a role. So this modulus of elasticity, E modulus, is orientation dependent. That's often neglected in calculations. So it also depends on in which direction my silicon is being stretched. Now, if it's a round membrane, a lot of these effects cancel out, so it's not so important. But if you have just a beam, the orientation of the beam in the crystal of your silicon also plays a role. And the difference can be quite significant. If you look at these curves here, this is of course plane dependent now, yeah, and so you have here 100, here you have a 130 or so gigapascal. Yeah? And this is true for silicon, but it's also true for germanium, for example. Yeah? So Young's modulus is also an anisotropic property. But it's just a side remark, yeah? Mechanically non-isotropic, anisotropic. Okay. So here you can also do more simulations. So here you have a square membrane where the simulation is actually only doing a quarter. Just looking at the graphics, you can see that this is a fairly old simulation here. Yes. Old simulations, they did use the fact that a quarter is symmetric. Well, it's enough to represent the entire. Okay. So this is done with finite element, and we use Copsol or Coventon these days, and that's fairly easy to visualize. And you see here now the red areas. There, the numbers of the stress is the highest. So that's the argument to put piezo resistors here and there, and over here and over there, and then I have my 4 locations for the Wheatstone bridge. And then I come back to the argument of pi L and pi T, 72 and minus 66.3, so comparable magnitude, opposite side. And that's exactly what I use then for the bridge configuration. So, here we go. I can do that. I can place them normal to the edge, normal perpendicular to the edge here. Yeah. I assume the diaphragm bends down, so pressure is from above, this direction. Yeah. And then I have this is being stretched longitudinally. So at the top of my membrane I have tensile stress, and sigma t is positive. If you go back here, sorry, no, that's sigma t, that's the stress, is positive. So I have tensile stress. So the surface, if I bend in this direction, gets elongated. Now, what about the transversal stress? So what I can use is this Poisson ratio again, B. And this Poisson ratio actually relates now the transversal to the tangential, not transversal to the longitudinal stress. So the Poisson ratio is a material quantity again. I can argue then the transverse stress is tensile and positive. This is my equation, my equation which we know now all the parameters. And now what I can do now, I can replace here one of the stresses through the Poisson ratio, and this here gives me finally my equation, how much change I can expect here if I put my piezoresistor like that. So the pi t is negative, and that means overall I get a resistance increase. And if I do it the other way around, it's the same argumentation, but if I do it like this, so blah blah blah, same argument, I get a decrease. So placing it like that, I get a decrease. Placing it like that, perpendicular, I get an increase. So that is what you exploit in a real pressure sensor. So the design is shown here: 3 piezoresistors, 2 perpendicular and 1 parallel, and the other one parallel here that has been cut off on a membrane. And I orientate these guys here along the 110 direction. So that's also something I have to take into account. Okay, so with that, I'll break before you run away. There were some emails to Newell that some of you, or for the groups, don't know each other. Are these persons here who emailed Newell that they didn't know they're members of their group? Yeah, it's always the same. Always the same or not here. And we can't help them. So you all know groups. You looked at the papers. Sorry?
I do not know my group.
You didn't know your group. Why not? You didn't get an email, or you didn't look on Toledo, or your groups are all.
They have to make their own group. They need to find their
Yeah.
I think we just have
member.
equation, right?
Yeah.
Okay. Yeah. Okay. So you don't have partners yet.
Yeah.
Anybody else who hasn't got a partner?
Can you raise your
One.
hand? Yeah.
Okay. So we have a group of. Usually it's
Can
3.
you raise your hand? The one who doesn't have a group
Yeah.
yet. Can you raise your
Guys,
hand?
who hasn't got a partner yet? Hands up.
Yeah, hands up.
1, 1, 2, 3.
So you can
three,
you
four,
you can look
six.
around between you and you can make.
So you 6 guys form 2 groups, please. Okay? Hands up again. Six people. 1, 2, 3. 6 people, 2 groups, huh?
Yeah.
Okay?
Yeah.
Okay, papers are on Toledo. And it's a first choice, first come, first choice. Huh? Okay, have a good weekend.